Now on BBC Two, we're hooked on local heroes.
Hello and welcome to Local Heroes from the Isle of Wight Ferry. This week, all my heroes come from the south of England.
My first hero was born on the Isle of Wight, and he had so many ideas he's been called England's own Leonardo da Vinci.
A man whose interests ranged from earthquakes to architecture, from plant cells to watches. If we can believe everything he claimed, he was more brilliant than Robert Boyle and Isaac Newton put together. His name was Robert Hooke.
Robert Hooke was born in freshwater Isle of Wight, but spent a lot of his life at the Royal Society as the first curator of experiments.
Just like Robert Boyle and Isaac Newton, Hooke had a law named after him, and it was about the stretching of springs. As he put it, in Latin, ut tensio sic vis, i.e. the harder you pull it, the more it stretches. Have a look at this. If I hang this spring here, you can see it doesn't stretch at all. If I hang a bag of oranges on an identical spring, it stretches about that much. But if I add another bag of oranges, hang 2 bags of oranges, you'll see that the spring will stretch twice as far as the first one did.
In other words, 2 kilos of oranges stretch a spring twice as far as 1 kilo, and 3 kilos stretch it 3 times as far. Hooke's law is important because it was one of the first ever mathematical laws of nature.
You may not realise it, but you're using Hooke's law every time you weigh anything, in the kitchen or yourself in the bathroom. Here's my bathroom scales. I weigh about 14 stone. And look inside. This little spring at the front is the one that's doing it. The harder you press on it, the more it stretches, and the more that dial spins round. So this is Hooke's law in action.
From his diary, we know when Hooke's sexual needs were catered for by his housekeeper Nell, because he wrote a special symbol. On later occasions, all perfect intimacy was provided by his niece, Grace Hooke. But however objectionable his sexual practices, he did invent the universal joint and the spirit level, and named the freezing point of water as 0 degrees.
And one of the most important things he did was to use a microscope, just like this one, to look at a piece of cork.
What he saw through his microscope looked like a cross-section of loads of box-shaped rooms, so he called them cells, and we now know that all living material is made of cells. But the really clever thing he did was to work out the true shape of the cells that he could see.
Hooke noticed a peculiar thing when he was looking at his cork, and I shall demonstrate it with the aid of this loaf of bread. Now, when he sliced it across like this, what he found was that the cells all looked like round circles, you see, it's like coins, and he wondered whether they were just flat or whether they were 3-dimensional.
The problem is that to see an opaque substance like cork under the microscope, it has to be sliced thin enough to be transparent. Hooke realised you then lose the 3-dimensional shape. His brilliant solution was to take another slice at 90 degrees, showing here that the apparently round cells aren't coin-shaped or ball-shaped, but long and thin, like sausages.
He described all his microscopic work in this wonderful book, Micrographia, or some physiological descriptions of minute bodies made by magnifying glasses by R. Hooke, Fellow of the Royal Society. And he starts with a really crawling dedication to the King, who was presumably rather short-sighted. Sir, I do here most humbly lay this small present at your Majesty's royal feet. And look at this, the flea. Nobody had ever seen a flea in such detail. Beautiful drawing of it. And all the ladies must have been horrified to see this disgusting creature magnified so much. He seems to have been a popular chap. He was certainly a good friend of Samuel Pepys and of Christopher Wren. Indeed, he helped Wren to rebuild London after the Great Fire of 1666. But unfortunately, he managed to get himself a bad reputation, and he certainly fell out badly, particularly with Isaac Newton. However, whatever his critics said, no one can take away the fact that he was the first person in the world to see and describe cells, the universal building blocks of life. If you're interested in Robert Hooke, there's a lovely reproduction of one of his pictures from Micrographia in the Local Heroes pack, and loads of instructions for experiments and things you can do at home. I'll give you full details at the end of the programme. One of the most famous engineers of this century did some of his critical research right here on Silvermere Lake near Byfleet in Surrey. He spent most of his life designing aircraft and airships, but he's best known for his bouncing bombs. His name was Neville Barnes Wallis.
Barnes Wallis started life earning 4 shillings a week in a shipyard, but he went on to be an engineer at Vickers.
Even before the Second World War started in September 1939, Wallis was thinking of ways to shorten it, and he fastened on the dams in the Ruhr Valley. He reckoned if he could knock one of those down, it would cause industrial chaos and seriously interrupt the German war effort.
His first idea was for a huge conventional bomb, but there was no plane to carry it, so he had to find a way of getting a smaller bomb in exactly the right place.
And then he had the brilliant idea that you might be able to bounce a bomb over the surface of the water to hit the dam, trickle down and explode right at the foot of the dam wall, and then the dam might just fall over. He knew that a stone would bounce on the water if it hit it with a contact angle of less than 8 degrees. But what about a great heavy bomb like this? Well, actually this is a tin of tuna, but this would be heavy enough to drop straight in if I dropped it, and I don't think I've got the strength to bounce that on the water just by throwing it. However, I have built myself a catapult here. And if you look, this is just a platform, and on the top of it there's a little carriage here which runs along, and it runs along when I pull this string. So I put my can in here, heave the string, it rushes forward and hurls the thing out into the lake. This is exactly how he did it, on this very lake, catapulting all sorts of things. They're probably still at the bottom in the mud. Okay, we put this on and make sure there's nobody swimming in front, and I get this round my hand and I give it a good heave like this. The other brilliant thing he did was to give it back spin. Now imagine, say, a tennis ball landing on a surface like this. Normally it would just bounce off like that, but if you give it backspin, it sits up, bounces much higher. And Wallis reckoned that the bomb would have a much better chance of bouncing if it had backspin. Also, if it was coming down like this, suppose it landed on one edge, then that would curl round and it would bounce off crooked, or maybe that way. But if he gave it backspin, then it would be gyroscopically stabilised, so it would stay absolutely on target all the way to the dam wall. Also, when it hit the dam wall, as it hit, it would bite in and go straight down like that and hug the dam wall, crawling down the dam till it got to the right depth and blow up in exactly the right place. There was one other problem to overcome, and that was the height of the aircraft. If the bombs were going to work, they had to be dropped at 230 miles an hour, exactly 60 feet above the water. Now, flying a heavy aircraft 60 feet above water at night was very difficult and very dangerous. The altimeters they had simply weren't good enough, so they devised an amazing new system. They mounted 2 spotlights in the belly of the plane, pointing downwards at the water, and as they came in over the lake, they switched them both on, and the spotlights converged exactly 60 feet below the aircraft. Then, when they were together on the surface, they knew they were at the right height. Have a look at this. Here they are coming in over the lake surface, and the bomb aimer looks down and says, down a bit, down a bit, down a bit, up a bit, steady, steady, down a bit, steady, bomb's gone.
The Möhne Dam was the first to go. Millions of gallons of water poured chaos into Germany's Ruhr Valley. Everyone said it couldn't be done, but Barnes Wallis had done the impossible.
There is no greater joy in life than first proving that a thing is impossible and then showing how it can be done.
My next hero was an ordinary Victorian commuter whose convenient invention gave people a lot of relief. His name was Arthur Ashwell.
On his daily commute from Dulwich to the City of London, Arthur Ashwell realised that the train conveniences were a bit too public.
For one thing, there was never a lock on the lavatory door, and so...
Say, do you mind?
Oh, beg your pardon. So it was pretty embarrassing. And for another thing, there was no indication on the outside as to whether it was occupied or not. These were the two problems that Ashwell solved in a flash, or if you like, with a bolt from the blue. And here it is. Here is his bolt from the blue. This is the bolt that's going to lock the lavatory door. So that's open and that's bolted. And you see it's attached as a rack and pinion mechanism, so that when the bolt slides, this wheel turns here. And the idea of that is that when the bolt is open, then there is no sign showing at the top here. But when you shut it, it says engaged. When they first install lavatories on trains, they often put one compartment on one side of the corridor, like this, labelled lavatory, and that has the lavatory in it. And then on the other side, they had another compartment labelled toilet, which has a wash basin in it, like the French toilette. That was where you washed your hands. But later on, the railway companies decided they couldn't afford to waste all this space. They could fit in more seats and more passengers. So they put the wash basin in the same compartment as the lavatory. And then they couldn't fit both the labels on the door, and so they just used toilet. And that may be why to this day, many people call a lavatory a toilet. My next hero was one of those brilliant people whose amazing skill covered half of science. He was the first person to show that light comes in waves, and he cracked the code of the ancient hieroglyphics of Egypt. His name was Thomas Young.
By the time he was 14, he'd already written his own autobiography in Latin. In it, he claimed he could read by the time he was 2 and had read through the Bible twice by the age of 4. Thomas Young did a lot of work on optics, but by profession he was a medical doctor, spending his summer in Worthing.
There was an argument going on about vision, and in particular how we focus on nearby objects. If I look at this shell down here, do I alter the length of my eyeball, make it longer, in order to get a sharp image of the shell on my retina? He decided to find out, and he used an instrument like this, a pair of dividers with rings on the end. And what he did was, this is pretty unpleasant, he slit one of these actually into his eye socket behind his eyeball, and then brought up the front ring to the front of his eye and measured the length of his eyeball. Then he did the same thing while he was focused on a nearby object. So he looked at this, slipped the back ring behind his eyeball, brought up the front one, measured it again, and it was exactly the same. So he proved that to focus on a nearby object, we do not lengthen our eyeball, and he concluded that what we must be doing is changing the shape of the lens inside. Young was interested in all sorts of things, but especially in light. Now, to show you this, we've got to come somewhere where it's fairly dark. So we're going under the pier at Worthing. There was a great argument about whether light was made of bits, corpuscles, or waves. He was sure it was made of waves, and he reckoned if it was, he could do an elegant experiment. What he did was to take light of a single colour, and he shone it through a pair of slits very close together. Now, I've got here one of those pointers that lecturers use, which has got a laser in it, you see, and here I've got a pair of very, very thin slits in a photographic slide.
There's less than a millimetre between the slits, so to see the two, you need a microscope.
So if I press that on, the red light from the laser shines straight through the pair of slits. And just look what happens when it goes on a piece of paper. Here we are. There, it just looks like a single spot, but as I move away, it seems to separate into dark and light bands. It's very weird, really. And what's going on is that these two slits are actually acting as two separate light bulbs, if you like, and there's waves going out from each one. Now, when those waves come together and the two crests come together, you get a very bright bit. But when the crest of one is against the trough of the other wave, then they cancel out, and it's just dark. And as a result, what you see out there is light, dark, light, dark, light, dark. They're called interference fringes. So Young did indeed prove that light comes in waves, and these have been called Young slits ever since.
What Young's slits showed us once and for all is that light is made of waves. But perhaps his most remarkable achievement was linguistic. A curious stone slab arrived in Deptford in 1802, and it's been in the British Museum ever since. The stone was found by a French soldier at Rosetta in the Nile Delta in 1799, and it's become known as the Rosetta Stone. The stone has the same message in 3 languages, but no one could decipher 2 of them. It took Young just 1 summer in 1814 to decode the stone, but as I've only got a couple of hours, I've asked the British Museum expert Carol Andrews to help me.
Now, it's fairly obvious even to me that there are 3 different bits of this, of which those are pictures.
Hieroglyphs.
Those are the hieroglyphs,
hieroglyphs.
yes. And this looks like Arabic.
No, this is Demotic. This is the 3rd and most cursive of the Egyptian scripts.
Okay, and this is Greek.
That's right. The Greek says that this decree was to be copied in Greek, in Demotic, and in hieroglyphs.
Is there something you can show me that says the same thing in all 3 scripts?
Yes, here we have the ancient title of the king of Egypt, Nisu Biti. Then we have the cartouche, the elongated oval containing the royal name, in this case Ptolemy, living forever, beloved of Ptah. In the Demotic, of course, the term for king is now Per-Ar. Per-Ar is our famous term pharaoh. And there is the king's name, Ptolemies.
Ah, okay.
And of course, in the Greek section, the Greeks used their word Basileus, that's king, Ptolemaios, that's Ptolemy.
So Thomas Young not only deciphered the ancient Egyptian Demotic language, he also did the groundwork for deciphering the ancient Egyptian hieroglyphs. Though he was a genius, Young died unhappy. He felt he'd never really made it as a doctor.
This is Ferox Hall at Tunbridge in Kent, where my next hero was born. She was the first person who ever put a photograph in a book, and her name was Anna Atkins.
She was born Anna Children in 1799. Her mother died soon afterwards, so she grew up close to her father, an enthusiastic scientist.
Anna became very interested in botany. Indeed, she was elected to the Botanical Society of London, which was one of the few scientific societies that admitted women members. They weren't allowed to speak, or they weren't elected to office, but they were at least admitted. And she began to collect seaweeds, both from her trips to the seaside and also from her husband, who had a coffee plantation in Jamaica and brought back exotic varieties. So she swapped them and built up a great collection. And she's decided to write a book about them and illustrate it with photographs. Now, I have to do this rather quickly. That goes off there, this goes on there like that. And then I put the glass on top and leave that to expose in the sunlight. Now, I'm using here the cyanotype process, which was invented by Sir John Herschel, who was a close personal friend of the family's. So he must have told them about it very early on. And you can see already the colour of the paper is changing. That's sensitized paper, and in the sunlight, the colour is changing, and these are going to be left as sort of silhouettes. But the great advantage of this process is it's very simple. It's cheap because it's based on iron and not silver. It's easy because you just lay the things down like that and make the pictures, and also you just wash them in water, and then finally they last very well, the pictures. Okay, I reckon that's about ready now, so I'm going to whip off the glass, whip off the seaweed, into the water, and wash it. And from this, I shall get a blue print. And indeed, the word blueprint comes from exactly this process. It's the same process, and they used them for engineering drawings for exactly the same reasons. They were simple, cheap, and permanent. Ah, look at that. Fantastic. Just in a few moments, the 2 different seaweeds, and you can see that this one is just a silhouette, but here you're beginning to see the structure showing up through the leaves. Isn't that beautiful? And it was with pictures like this that she illustrated her book, the first book ever to have photographs in it.
Her later book, cyanotypes of British and foreign flowering plants in 1854 showed as many as 160 photos, not just of her seaweed collection, but of flowers and even feathers.
Anna died at the age of 72 and was buried right here in Halstead along with her husband. But on his side of the stone it says that he was a justice of the peace and did all sorts of things, whereas on her side it merely says that she was the daughter of John George Children. It doesn't even mention the fact that she was the first person ever to put a photograph in a book. And unfortunately, that was often the case with women. They were so often ignored. However brilliant they were as innovators, scientists, pioneers, nobody paid any notice. So if you know of any brilliant heroines, please write to me about them at the BBC or send me an email. Some of my heroes most people have never even heard of, but this man is world famous. He showed how natural selection can explain evolution, and he wrote a famous book on the origin of species. He is Charles Darwin.
Charles Darwin was born at Shrewsbury in Staffordshire, where his dad was a doctor. He went to Edinburgh to study medicine, but he couldn't stand the sight of blood. Then he went to Cambridge to study theology, but he much preferred collecting beetles. When he was 22, against the wishes of his dad, he took the position of unpaid naturalist on a ship, the HMS Beagle. The discoveries he made sailing around South America changed forever the way we think about the world.
This is the bird collection of the Natural History Museum in Tring, and I've come to look for the most exciting scientific relics I've ever seen. When Darwin sailed on the Beagle, most people thought that the world had been created exactly as it is in 4004 BC. And then he came to South America and it was full of plants and animals, and he wondered where they'd all come from. And then they sailed west from South America to the Galapagos Islands, right out here in the Pacific. And they were black, volcanic places. He stood on one little hill and he could count 60 black cones. And he said they reminded him of the iron foundries in his native Staffordshire. And there in the Galapagos, he shot a whole lot of specimens, and the birds are here. And here, look, floor 1, case 13, Darwin specimens. Just look at this, is really quite something. Darwin finches, Galapagos. These are the actual finches that Charles Darwin shot in the Galapagos Islands in 1835. That is absolutely amazing. Now, I'm not allowed to touch these, partly because they've been preserved with arsenic, but I'll take out this box of 3 and bring them over to show you. And if you have a look at these 3, you can see that they're extraordinarily different. They are all finches, but the top one is very tiny. It's sort of browny green and it's got a little pointed beak, slightly curved. The one in the middle is mottled and it's got the same sort of length beak, but it's much chunkier and tougher. And the one at the bottom, the black one, is at least twice as big as the top one, and it's got a huge great beak, almost like a parrot. And if you think about it, think of these pliers. Here are some delicate pliers with a pointy nose, perhaps used for model making or something like that. And you can imagine that if these pliers were hungry, they might eat a worm or insects or something like that. If you were to think of these pliers, these are about the same length, but they're much chunkier. They're more like the middle beak here. And they might be able to cope with, say, a hazelnut, some small, or seeds or something like that. Whereas if you look at the big one at the bottom, it's almost like a parrot, and you can imagine that these pliers are sort of analogous, and you could obviously cope with a great walnut with that and crunch your way through it. The pliers have clearly been designed to do different jobs, and Darwin mused that the same sort of thing might be true for the finches. He said, one might really fancy that one species had been taken and modified for different ends. This is Down House in Kent, where Charles moved with his wife Emma in 1841, and he carried on puzzling about how these changes happen and where new species come from.
On most days, he took a constitutional in the sand walk he constructed in the wood near his garden.
And while he walked here, he was thinking about an essay he'd read, an essay by Thomas Malthus on population. Malthus said that in any human population, babies will go on being born and the population will increase until they run out of food. And then people will start dying because of starvation, disease or war. And Darwin realised that this must be true for animals too. Exactly the same principles apply. And this idea might be the key to unlock that puzzle of evolution, which he went on thinking about for more than 20 years.
So here at his sandwalk, he thought about human populations, plant populations, and those Galapagos finches. And so, in the end, he worked out where we all come from.
Now suppose that one pair of finches produces 10 babies. Then those babies are bound to vary. They always do, kids in a litter. And some of them will have smaller beaks than their parents, and some will have beaks that are a bit bigger. Now imagine a year in which the food runs very short. You remember Malthus. Then the ones that are better able to find the food and cope with it, that is, the babies with the biggest beaks, will naturally get the most of the food because they'll be able to bite into the nuts, and they will grow bigger and healthier, they'll find mates, and they themselves will be the successful parents. They will, if you like, be the most fit for the environment. Now, in the next generation, we've got bigger beaked parents. And of course, the same thing may happen again. In the next year, if food is short, again, some of their babies may have smaller beaks and some bigger, and again, it'll be the bigger ones that survive. So gradually, over a long period of time, you're liable to develop finches with bigger beaks. Of course, in other parts of the islands where there are seeds to eat or insects, some other sorts of finches will develop smaller beaks. But the basic thing is it will take a long, long time. And when the survival of the fittest happens over generation after generation for maybe 1 million years, then you may develop a new species. The implication of that was absolutely staggering. If you have heredity, variation among the offspring, and a shortage of food, then you are bound to get evolution. And evolution, just natural evolution by a random process, has produced every lion, every lamb, and every leaf on planet Earth. By showing that one species must have evolved, Darwin realised himself that all species must have evolved. And that really shocked him. He could scarcely believe it. He sat here in his study and he worked on his ideas, sitting in this chair, writing on this board, with all his filing system here behind him. And eventually he was kicked into action in 1858 by a letter he got from Alfred Russel Wallace, who'd come to much the same conclusions. They published a joint paper, and then in the following year, Darwin published his massive book on the origin of species by means of natural selection. They printed 1,250 copies at 15 shillings, and the whole lot sold out on the first day. The book caused a tremendous storm because it implied that people must have evolved, and horror of horrors, from apes.
But that was only a tiny part of arguably the most important and most elegant idea in the whole of science, the principle of evolution of species by means of natural selection.
Sorry, that's all for this week. See you next time.
You can do some experiments from this series and the last one with our Local Heroes kit. We don't make a profit, so it's only £9.95. You can order by credit card by phoning 0990 100 789 anytime, or write to Local Heroes Kit, PO Box 7, London W12 8UD, making your cheque payable to BBC Education. And why not visit the Local Heroes website?
Adam Hart-Davis gets on his bike again on Thursday looking for more local heroes. He'll be pedalling back onto BBC Two at 8. That's except for viewers in Scotland.